in this case, the one thing I would say is just remember, like, if you're getting delayed for some reason, like a mechanical problem, we all are like, we feel a little better about the mechanical problems because we realize we do not want to get on a plane that's a little sketchy. But like if it's weather or something like that, that's also something, don't push them because you don't want to take a chance, right? If that was a United flight, United helicopter flight, there's no way they'd go probably because they'd be like, there is a 1% chance that we might not make it, and they aren't going to take that chance, right? The other thing I want to tell you guys about is this. If you're connecting to another country or taking connecting flight, then what the stewardess told us is, because we did not make our flight out of LAX from SFO. We missed it completely because of the stupid fog. So the first thing is, if you're going to be doing that, don't fly out of SFO. Fly out of Oakland or fly out of San Jose because they don't have fog issues. So that's the one thing I would kind of tell you about. Don't do that. And I mean, even if it's like $15 more, I would say if you're connecting to Singapore, right? Totally would have been worth it. The second thing is what the stewardess told us was if you're flying somewhere else, you ideally want to be in that connecting city before you go overseas. You want to be there like the night before, or at least several hours before, so you have a little bit of flexibility. So it's something I always try to cut it kind of fine. I need an hour and a half in between, so I try to make it an hour and a half because I don't want to waste my time. But you miss one big flight that's really important, like going to going to Tokyo. It was actually Tokyo. We came back from Singapore, and it was terrible. They ended up, Singapore Air said, "Oh, well, we can get you." They finally found us a spot that would land in Tokyo 2 days later, 2 hours after our cruise ship left. It's like, well, that's no good. So we ended up finding something else, but still it was a whole nightmare and all sorts of other things and stuff like that. So, and my sister's bag got lost. So the other thing is, you guys all know this. When you pack, one is, if you can at all possible, don't check luggage. Right? My friend worked for United. She's like, never check luggage. But the other thing is, make sure you keep a change of clothes with you, ideally for a couple days. All of your medication should be with you. Right? My sister had her medication in her checked luggage, which was a nightmare. And she had no clothes. So, I always bring my toiletries and my socks and underwear and a couple of shirts or whatever, so I'm good for a couple of days. Those are my two things. They're not related to math at all. But, so I'll do that once in a while. Just things I think are important to point out or bring up. All right. Multiplication rules and conditional probability. Stefan, have you read yet? Go ahead.
The multiplication rules and conditional probability. Two events A and B are independent events, but the fact that A occurs does not affect the probability of B occurring.
Right. So the fact that one occurs does not affect the probability of the other one occurring. So here's an example. You see my probability structure. Guys can explain it to me. Does drawing a heart give you any information about whether it's king? So what's the probability to draw a king? Here's a bunch of cards. What's the probability to draw a king?
4 to 52.
4 out of 52. So probability of king, so again, probability capital P of parentheses king is 4 out of 52. Simplifies to 1 out of 13. Now, what if we care about hearts and kings? So what if you know it's a heart? So the event heart has occurred. So I'm telling you, oh, you draw a card. I look at your card. Oh, your card's a heart. So given it's a heart, I'm giving you that information. You now know it's a heart. It's one of these 13 cards here. What's the probability that it's a king?
1 out of 13.
Yep, 1 out of 13. Good? So 1 out of 13. So this is what we call probability of a king, given it's a heart. 1 out of 13. So again, just to point out, it's probability of king in both cases. Just one is probability of king given nothing, the other is probability of king given it's a heart. since these two probabilities are the same, right? Probability of king hasn't changed. It's still 1 out of 13. Then we'd say it's independent. Because knowing it's a heart has given you no information about whether or not it's a king. Right? You still have a 1 out of 13 chance of having a king. Okay, change the deck. Here's my deck. Great. Here's the king of hearts. Right? I toss it out of the deck. It's gone. Now, I have 51 cards in the deck. How many kings are in the deck?
3.
So what's the probability I draw a king?
3.
3 out of 51. Good. So probability of king is now 3 out of 51, which reduces to 1 out of 17. What's the probability of, okay, so now you draw it and I tell you, oh, your card is a heart. What's the probability your card's a king?
0.
0. There are no king of hearts, right? So here, the probability of a king, given it's a heart, is 0. Has the probability of it being a king changed?
Yes.
So these would be dependent. Does that make sense? So the event king and the event heart affect each other in this case because there's no king of hearts. So they would be dependent. Likewise, if we added extra hearts, kings in there, like if we had like 4 king of hearts in there and stacked it with lots of kings of hearts, it would also not be, it would also be dependent because it would change things. All right, you guys are really quiet today. No worries. What if I take 5 cards? We're going to look at something slightly different. Ace through 4. 5. Ace through 5. Right? Hearts, ace through 5. Everyone else on board with that? And I'm going to mix them up. Have somebody draw. What's probably she draws an ace? 1 out of 5. Draw a card. Okay. Put it back. Mix up again. Now it's probably she draws an ace. 1 out of 5. Okay, drop, don't look. Don't look. Now, what's the probability she draws an ace? 1 out of 4 because she didn't put it back. Or it could be 0 out of 4 depending on what she but what her probability depends upon her probability. It's either 0 out of 4 or 1 out of 4. Either way, it's not the same as 1 out of 5. It's changed. Everybody see that? So that's dependent. So when you draw a card and you replace it, and when we replace it, we mean you replace the same card. Then they are independent. But if you don't replace them, then that becomes dependent. Make sense? So a lot of times we're going to be talking about, most often we're going to be talking about marbles. We'll have marbles in a bag. And you draw a marble, you look at it, and then you replace it. Does not mean you replace it with some other marble. It means you take that same marble and you replace that same marble back in the bag. So we'll be doing that a lot coming up, just so you understand what that means when we say that. All right. Good. What about if I flip a coin and roll it out? Okay, so here's my die. What's probably rolling a 4? 1 out of 6. Everybody on board? Great. Now, 1 out of 6. Now, I flip a coin. Oops. Flip it again. Do it better so I get heads. Great. I have heads. Now, what's the probability I roll a 4? Still 1 out of 6. So, understand that? Because flipping a heads is independent of rolling a dice. They have nothing to do with each other. They don't affect each other. So those two things would be independent. Make sense? So these two things are independent, those two events, because they don't affect each other's probabilities. All right, so won't you guys take a minute? Well, actually, we'll do this together, actually. That's better. Chocolate and mail. So first, let's find the probability of chocolate. Everyone find the probability of chocolate, and then find the probability of chocolate given their mail. Find those two things.
No, she just slipped out.
All right, so what's the probability that you pick a puppy and they are a chocolate lab? 8 out of 20. Good, so that's about 40%. Now, what's the probability that given they're a male? So given it's a male puppy, now what's the probability that they're a chocolate lab?
6 out of 12.
6 out of 12. Oops. 5. So, are these the same?
No.
No, the probability has changed. So it means that they're dependent. Knowing that the puppy's a male, all of a sudden the probability of their chocolate has changed. It used to be the probability of chocolate is generally that they're 40% chance you're going to pick a chocolate lab. But if you know it's male, it jumps up to 50% chance. A lot of chocolate labs in this. Now that's not about the whole world. We're not talking about the entire world of puppies. We're talking about just this sample. From this sample, you know that if it's a male, there's a 50% chance it's a chocolate lab that you're going to grab. Is everybody on board? Please note, you're not comparing the probability of chocolate to the probability of male, because that's not fair. That's like, is it fair to compare the probability of rolling a 4 to the probability of getting a heads? Does that make any sense at all? No, it should be probability of rolling a 4 to a probability of rolling a 4 given I've done something else. I've flipped a heads. So either way, it has to be the same. Probability of chocolate, probability of chocolate. This is probability of chocolate given nothing. Probability of chocolate given the other event has occurred. The male event has occurred. It's male. If they're the same, they're independent because this hasn't affected it. If they're different, then they're dependent because this has affected it. In this case, it has affected it. Let's go through another one. Why don't you guys try this one? So this is page 5 on your notes. Is that right? Take a minute. Find these probabilities. See what you get. Given it's male, you know it's a male. You know it's a male. Circle. So because you know it's a male, you know it's one of this group. And now you do the chocolate.
Because you can repeat, right? So it's 4 out of 4 was 2.
Whenever you have the givens and you have a table, always circle, you guys. Always. Whatever given is the part you should circle. It just makes life easier. So here, what's probably that your puppy is female? 8 out of 20?
Yes.
And then female given yellow. So whenever you have given, that's the part you circle. What's given? Yellow or female?
Yellow.
Yellow. So circle the yellows. Do you guys see what I'm saying? Actually physically circle it. And then it makes it easier. What's the probability that they are yellow? Female? So a female? 4 out of 6, right? It just makes it a lot easier. Is it hard to circle? No, it takes like an extra half a second. Just make your life easier. Here's something else that one of my students pointed out, is see how this line looks like, kind of like a dividing sign? Right? Everyone see that? So if you kind of wrote it like that, because everybody is okay with this 4. They get the 4, right? That's not the problem. Sometimes they want to divide by the 8. Do you guys see the 8 over here? And they're not sure which one to divide by? Divide by the yellows. How many yellows are there? 6. That helps you figure out what to divide by. The numerator is always going to be the female yellows. But the dividing by part, a lot of times we'll have trouble with that. So she said, oh, well, I think of this as a dividing sign, and I divide by the yellows. So that was from like 3 years ago, 2 years ago. That was a good hint. People kind of like that. Okay. Another way of looking at it is this, looking at ratios or proportions. So, what are the things I care about here? Obviously female, right? Female yellows and females, and then also care about yellows, right? And what's my total? 20. Should have that also. So you can think of it like this. I'll do a new one. 4, 6, 8, and 20. And one way of thinking about it is doing 4 over 6 compared to 8 over 20. Just find those ratios. Is 4 over 6 equal to 8 over 20? And that's a no, so they're dependent. Do you guys see what we just did there? I'll go back to the last one, the first one. I'll show you that one too. So what do I care about? Male and chocolate. So which ones do I care about when I'm looking at male and chocolate? Let me put in the 20 here. What numbers do I care about, guys? With your neighbors, 15 seconds. Figure out the 4 things that are important with male and chocolate. The total being one of them. All right. Ulysses, give me one.
Answer?
No, give me one thing that I want to circle.
Female?
I'm sorry? Chocolate and male we're talking about here, right?
Yes.
So give me,
Circle will be the sex, the male.
right here, this
Yeah,
12 or
yeah.
that 12, or which one of these?
The whole thing.
Nope, just one, the last one. So the total of the males. Someone give me another one. Jay, give me another one.
6.
Which 6? That one, or the first, second, or third one?
First one.
The first one, because it's the male chocolates. Make sense? Male and chocolate, it has those in common. Chocolate and male, that's what we care about. Jacob, give me another one.
The total?
The total, great. And the last one, Armida, give me the last one. It always sort of makes a rectangle too. 8. Yeah, see that makes a rectangle? So we have the chocolates, we have the chocolate male, we have the total chocolate, we have the total male, and we have the total total. So everyone see those 4 things? So then we can either compare 6 over 8 to 12 over 20. Right, so this is the problem with chocolate, 6 over 8. No, wait, that was the male given chocolate. We didn't do that one. So we can compare these two and say, are they equal?
No.
No, so it's dependent. Or we could go the other way. We could go 6 over 12, right? 6 over 12 and 8 over 20. 6 over 12 to 8 over 20, and see if these are equal. And that is also a no. So those are always be the same. Either they're both equal or they're both not equal. So you can compare either one of those. So this is by using the proportions. right? Chocolate out of the total to chocolate males out of the total males, given its male. So you can do either one of those ratios instead if you prefer that. But that's the question you should be asking. Is that 6 over 8 the same as that 12 over 20? That top, up top, that's the one people usually grab because it fits so well, right? One over the other, this one over this one equal to this one over that one. That 6 over 8 equal to the 12 over 20. Do you guys see that? Okay. So this is a more common one. 6 over 12. I won't do that. That's confusing. So this would be 6/8. This would be 12 over 20. Right? Anyone? Yes? No? Okay. I don't know. We should keep explaining, or I should just stop. Stop. Okay. All right. I'll stop. Just stop. Please stop. All right. This one is known as chocolate. Change your guess about whether it's female.
Yes.
So find the probability it's female. Find the probability it's female given it's chocolate. Find those. 15 seconds. This is the last. I guess the top of the next page, right?
Yeah,
Top of the next page.
it's on the back side.
Find those two numbers. I'd be happy to calculate and figure out the actual numbers.
So is it 3 and 15 because it's female? And then it's female.
But as soon as the probability of female, so that would be just a female over. But if it's not just different chocolate, the total chocolate is
Or this way.
yeah, because it's different numbers divided by that.
So what did you get?
Yes, yes, yes.
Did you get 15 over 40?
Yeah, so this one is 15.
15 over 40, right? And this is going to be over 8?
Over the total. And then it says 8. Because it's giving me the 8. Which is the chocolate.
Because you know how she said that the chocolate is on the bottom, so you just divide it.
So did you get 3?
Yeah, I got
3 over 8.
Yeah.
So passing this class is a very, very simple formula. Passing this class is basically doing the problems and understanding the problems you're doing in class. If you do the problems in class and understand them, piece of cake. Super, super easy. If you,
no,
what?
I'll give a lot more.
Edgar says he wants to rebuttal it.
And understand them.
Like, as a at least.
Okay. So what's the probability that they're female? 15 out of 40. Now, this is given chocolate, so it means you should be dividing by the number of chocolate people. So, chocolate lab, sorry. So what's the probability that it is a female given it's a chocolate lab? 3 out of 8. Why? Because how many chocolate labs do we have? 8. Good? You could also have found these 4 numbers. Female, total chocolate, total female, total 3 8s, 15 and 15 40s. See how they kind of jump out right there? All right, are these the same? What's this?
Yeah.
Yep. They're both 0.375. So, are female chocolate independent events or dependent events? Independent events. Everybody got that? Because knowing it's a chocolate lab has not given you any information about whether it's female. Same with the cards, the kings and the hearts. And you just compare those two probabilities. All right. So now we get to the multiplication rules. Read go ahead and read the first multiplication rule.
It's the probability of A and B equal to the probability of A multiplied by the probability of B.
Perfect. If they're independent, you just multiply the probabilities. Great. Do you want to take a shot at the second one? Or no, let somebody else do it. Let's somebody else. He's gone. Alyssa. Oh,
The dependent,
this one. Yeah.
the probability of A and B equals the probability of A times the probability of B and A.
Given A. Nice. Well done. If it's dependent. So, if it's independent, you just multiply their probabilities. You have to, because you have to pass both tests. If they're dependent, then you find the probability of A. So it's like a tree. You take a step towards A, and then you find the probability of B given A has happened. So the probability of B given A has already happened. So that's why you have to do that. If A affects B, then you know A has happened, so it's probably a B given that A has happened already.
So going back a slide, they're independent?
What was that?
Going back a slide, they're independent?
Yeah, these two are, because the
They're the
probabilities are the same.
Okay.
And again, remember, this conditional probability, it means given A has happened. All right, so, lab 3. A coin is flipped and a die is rolled. Flipping a coin, rolling a die. Did we say those are dependent or independent? Independent, great. So, piece of cake. Draw a tree for that. So first, you're going to flip a coin. How many outcomes are you when you flip a coin? 2. So you better have and make it big. Use up a lot of space because you need to have room for the other ones. And then you roll a die. So if I flip heads, what can happen next? I roll a die. How many outcomes are there? 6. If I flip tails, I roll a die. How many outcomes are there?
6.
Good. All right, draw your tree.